Section 16.5 Strong Acids and Bases. The chemistry of an aqueous solution often depends critically on the pH of the solution. It's therefore important to examine how the pH of solutions relates to the concentrations of acids and bases. The simplest cases are those involving strong acids and strong bases. Strong acids and bases are strong electrolytes, existing in aqueous solution entirely as ions. These are relatively few common strong acids and bases, as we have listed these substances in Table 4.2. Strong acids. The 7 most common strong acids include 6 monoprotic acids: hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, chloric acid, and perchloric acid, and 1 diprotic acid, sulfuric acid. Nitric acid, HNO3, exemplifies the behavior of a monoprotic strong acid. For all practical purposes, an aqueous solution of nitric acid consists entirely of hydronium and nitrate ions. Nitric acid plus water yields hydronium plus nitrate ions, complete ionization. We have not used equilibrium arrows for equation 6.2.1 because the reaction lies entirely to the right, to the side with the ions. As noted in section 16.3, we'll use hydronium and proton aqueous interchangeably to represent the hydrated proton in water. Thus, we often simplify the equations for the ionization reactions of acids as nitric acid yields protons plus nitrate. In an aqueous solution of a strong acid, the acid that is normally the only significant source of hydrogen protons. As a result, calculating the pH of a solution of a strong monoprotic acid is straightforward because the concentration of proton equals the original concentration of acid. In a 0.2 molar solution of nitric acid, for example, the concentration of proton equals the concentration of nitrate equals 0.2 molar. The situation with diprotic acid, sulfuric acid, is more complex, as we'll see in section 16.6. Strong bases. There are relatively few common strong bases. The most common soluble strong bases are the ionic hydroxides of the alkali metals, group 1A, and the heavier alkaline earth metals, group 2A, such as sodium hydroxide, potassium hydroxide, calcium hydroxide. These compounds completely dissociate into ions in aqueous solution. Thus, a solution labeled as 0.3 molar sodium hydroxide consists of 0.3 moles of sodium and 0.3 moles of molar hydroxide. There's essentially no undissociated sodium hydroxide. Although all these hydroxides of the alkali metals group 1 are strong electrolytes, lithium hydroxide, rubidium hydroxide, and cesium hydroxide are not commonly encountered in the laboratory. The hydroxides of the heavier alkaline earth metals, calcium hydroxide, strontium hydroxide, barium hydroxide, are also strong electrolytes. They have limited solubilities, however, and are only used when high solubility is not critical. Strong basic solutions are also created by certain substances that react with water to form hydroxide. The most common of these contain the oxide ion. Ionic metal oxides, especially sodium oxide and calcium oxide, are often used in industry when a strong base is needed. The peroxide reacts with the water to form hydroxide, leaving virtually no peroxide remaining in solution. O2- plus water yields 2 hydroxides. Thus, a solution formed by dissolving 0.10 moles of sodium oxide is enough water to form 1 liter of solution will have a hydroxide concentration of 0.02 molar and a pH of 12.30.